Evening everyone. Welcome to the webinar. We will be starting shortly. So my name is Rakshit. I'm a core committee member of CodeChef-VIT, and as you all know, data structures has a very important role in our coding life, and stacks and queues are one of the most basic elements of data structure. So today we will be discussing stacks and queues. I will be starting shortly. 1 minute. So we are good to go. The first concept today which we will be discussing is stacks. Stacks, we will be discussing these three topics: introduction to stacks, parenthesis matching, Tower of Hanoi. Just response with yes if I am audible. Just once response with yes if I am audible. Okay, we are good to go. The first topic is introduction to stacks. Basically, stacks is a collection of data with a restriction that the data can be inserted or deleted from one side only, which is known as the top of the stack. So, as the figure shows, these are some of the plates kept in a restaurant, maybe anywhere. So, if the server has to take out a plate or put a plate, he can only put it on the top of the stack, the top of this pile. So, only the first plate which is accessible is the top one. So, stack follows LIFO or FILO. LIFO is last in, first out. So last in. So last in was this top plate. This was kept at the last, and this one will be the first one to be served. And first in, last out. So as I explained. So this is basically what stack is. These are some of the basic examples, real life examples of stack. Like, this is a toy of a child. The child cannot access the green ring until he take out the orange one. Similarly, this example is the example of Tower of Hanoi. I will be discussing it shortly. And in this train picture, you cannot access the red colored container until you take out this green color container. Now, before showing you the code of stacks, I would like to brief up you upon some of the basic terminologies of stack. So, three main basic terminologies are there in stack, that is push, pop, and top. So push is when you have to enter any data in the stack. Obviously, the data will be entered from one part only, from one side only. As shown, the data can only be as shown in the figure in the right, the data can only be entered from right side. That's the top of the stack. So that's push. Now comes the situation of overflow condition. Overflow condition is when the stack is full, when there is no space in the stack. Obviously, the stack cannot be infinite length, has to be of a limited length. So when the length of the stack is full, then it is overflow condition. And same pop can only be done from the topmost element can only be popped. And underflow condition is when the stack is empty, there is no element to pop, so what will you pop? And top refers to the most uppermost element, which is most prone to be popped. So this is a basic stack. This is the empty stack at the leftmost corner, and then we push element A. So it is at the top of the stack. Then we push another element B, that is now above this element A. So B is above A. And now we are going for pop. Pop means take out the element. So we take out the topmost element of the stack, that is B. So the element left is A. Now we again push an element. The pushed element is element C. So the configuration is C, and below that is A. Now we again pop. So the topmost element C is pop. And one more thing which I want to tell you, I'll tell you using a diagram. Just so let's say this is a stack. I will say the size of the stack is 2. I will number it 1 and 0 and 1. So at the beginning, the top is at -1 position. At the beginning, the top is at -1 position. Okay. This is the thing, that when we are starting, the top is at -1 position. Now let's rush to the code. Yeah, I zoomed it. Problem. So as you can see, I am highlighting it. I have declared top as -1, as I told you in the description now. And we have taken the size of the stack, as the stack cannot be infinite. So we have taken the size of the stack. Then we have also defined the stack, obviously. Then we have applied a do while loop, and we are taking the preferences from the user. These are the three preferences: push, pop, or display. Display is nothing but he will display the whole stack, obviously in the order in which the definition I have told. And we have taken, so we are applying a switch case. If you want to know more about switch case, you can refer to our previous videos on the same channel. And case 1, so 1 is push. So case 1, first condition which we will be following is top is greater than size -1. Obviously the top cannot be full. If the top if the stack is full, then we cannot push anything. So that's the condition which I told you. And if the stack is not full, Then using a for loop, we can just enter the values. We can take up a value using variable 1. I've taken that, you can, and we can just place that variable 1 on stack top. Yeah. So here ends NQ part. Now comes DQ part. So in DQ, first we are checking that underflow condition. What if the stack is underflow? So first we are considering that top is, if the top is equal to -1, as I told you here, that if the top is equals to -1, that means that the stack is empty. So we will write that, sorry, stack is empty, you cannot pop anything. Else we can just pop the topmost element. We can just pop the topmost element, and we can do top -1. Going forward, this is the display. We use a for loop for displaying the whole stack in the order as defined in the definition. So just let's run this code. So for simplicity, I'm just taking the size of the stack as 3, and it is asking for preference what I want to do. Obviously, I will do a push for. I'm entering the value as 9, 8, 7. Good to go. It is asking anything more you want to do. Yes, I want to pop. First, I will do a display operation. So let's go for display. So see, 7, 8, 9 is displayed. I entered 9, 8, 7, but 7, 8, 9 is. So it is following the rule and it is displaying that element which I inserted last. So the first, last in, first out is satisfied over here. Now let's pop each of the element and see. So the topmost element is 7. We go again. Topmost element is 8. Go again. Topmost element is. So this means that the our code is good to go. Any doubts can be addressed. Please put the comment section. So, done. So we will move further. So the next thing in our is parenthesis matching. So basically parenthesis matching is a string expression will be provided to us, and we need to examine is if the pairs and the order of the brackets are correct in the expression or not. I will show you algorithm how it works, but let's first see some test cases out here. Yeah, so the first one is these 3 open brackets and then the same 3 close brackets. So it is balanced. Give me a, yeah. And in this case, these 3 are open, but they are not closing. Only one is closing. So it becomes unbalanced. In the third case, they all are opening and they all are closing. But if you have a notice that the last 2 have changed their position. So as per the definition, the order is also to be the same. So we cannot apply that. So now I will just brief up about the algorithm. First of all, we have to declare a stack for doing this, and if an open parenthesis come, this is the open parenthesis. When open parenthesis come, you have to just push that into the stack. And if a closed parenthesis come, the closed parenthesis come, then you have to see that if the top of the stack is the corresponding to that open parenthesis, then you have to pop that from the stack. I will explain it better with an diagram. So initially we have declared a stack and empty stack, and then expression is being provided to us. So the first part of the first element, that is nothing but an open parenthesis. So we push that. Similarly, the second part, it's a open parenthesis, so we again push that. And the third part is an open parenthesis, so we push that. So at step 3, the stack is this. Now comes the fourth element of the expression. This is closed parenthesis. Closed parenthesis means now we will check that whether the top of the stack is corresponding to the closed parenthesis or not. So as you can see in the step 3, the closed parenthesis has a corresponding top of the stack. They both are corresponding to each. So we pop this out. Similarly, we pop this out also, and similarly this. So it would be better if I show you the code also. Good to go. So first we have declared a stack, and we are asking the user for the expression. You can see about line 7 and 8, and then comes a for loop. We are running that for loop from 0 to the string length, or the length of this expression which we have taken in from the user. And then comes a condition, if condition, that is if the ith element of the expression is an open parenthesis, any open parenthesis, we have 3 of them, any of them, if it is an open parenthesis, we have to do nothing but we have to push it into the stack one after the other, obviously. So, and we have to top plus plus, that's the increment. But in the else if case, I have put that if the expression, or if the parenthesis is a closing parenthesis, then we have to check that if the expi is equals to this open parenthesis, which means that if the expression is this and the corresponding top of the stack is the closing parenthesis corresponding to that, so then we have to pop. Similarly, I have done for this, similarly for this, and at last, if the stack is empty, which we see using top is equals to -1, then we can print that the parenthesis has matched, or else we can just and at last, for just checking what is the top value, I've put a printf statement. Let's run the code and check. So I will put a expression which we saw in the example. So it shows stack is empty, hence parenthesis is matched, and top value is -1. So our code is correct. Now let's run this one more time, and we will put a wrong input this time. So this goes like this. So as you can see, I've not closed one of them. So let's see what will happen. So it shows stack is not empty, parenthesis has unmatched, and top is 0. So since top is not is equal to -1, stack is not empty. So we have done parenthesis matching also. Yeah. So out of this, we have done introduction to stacks and parenthesis. If you guys have any doubts, please put it in the comment section regarding parenthesis matching or introduction to stacks. Showing that you guys don't have any, so let's forward because cover a lot. Whew. So now comes Tower of Hanoi. I showed you this. I showed you the picture. This is the picture which I am talking about. Right bottom picture, Tower of Hanoi. And let's discuss what Tower of Hanoi is. So Tower of Hanoi is a mathematical puzzle which consists of rods and discs. There are only three rods, n number of discs. So the objective is to carry these three discs from the source rod to the destination rod using any of the random transitions which we want to do. So, but there is a flaw in this, that we have to follow some simple rules, that only one disk can be moved at a time. So you can only move that first disk one at a time. Second is that disk can only be moved if it's at the uppermost. Obviously it is application of stack, so we can only pop the topmost element. And the third point is no disk may be placed on the top of a smaller disk. So this means that 2 can be placed over 3, but 3 cannot be placed over 2 because 3 is bigger in size as compared. So our thing is that we have to take all these 3 disks to the destination rod. We can use this auxiliary rod. So I am considering these 3 disks only. Let me take a pen. I'll take a good color. Blue is my favorite color. So we have to carry these 3 disks from A to C, as you can see. So in the first case, we carry this topmost red disk to C. Carry this to the C. So this is the scenario, that 2 disks are here and C is here. Now we carry this third disk to B. So this becomes the scenario. All the 3 disks in different rods. Now we carry the C disk to the B disk on it above. English. So this becomes the scenario. Now we carry this third disk to the C rod, the last rod, final rod. So this becomes the scenario. And now only one part is left, that we have to carry these both on top of this. But according to rule number 1 or 2 maybe, we can only carry one by one. So we follow that, we take this red disk on A. So fifth one becomes the scenario. And now we carry this second disk to the third rod. So sixth becomes the scenario. Here you can see. And now we carry this A disk to the C. So we reach our final disk. Now the point is that we had 3 disks and the total transition took is 2 raised to power n minus 1. Total transition. I have not included in the PPT, where n is the number of disks. Got it? So this was Tower of Hanoi problem. Now let's see the code of it. One more thing I want to just tell you. You saw that this means that there is a same function which is performing of carrying one disk to another. Carrying one disk from any rod to another rod. This function is repeated. So don't you think that this is a recursive thing? Recursive function types. And let's see the code. You'll get to know what it is. So just Tower of Hanoi. Small code, very small. So let's come to the main thing. We have declared n will be the number of disks. We are taking it input and we are sending it to a function known, I have written as the Tower of Hanoi. And write it in. We are sending 4 values, n, a, C and B. A, C, B are the rods and N are the number of discs. So void tower of Hanoi, we have taken all these things. We have taken from rod, from the initial rod as A, um, the middle rod as B, and the final rod as C. And a condition is that if there is one stick only, one disc only, then only one transition will take place, and which one will be this, and rest this will be followed. So let's just check it out and see that what I explained to you was correct or not. So I will check it for 3 discs, and let me just check. Yeah, good to go. So it shows the same result which I just showed you, which I just explained you using that picture in the PPT. So this means that the code is good. I have given the resources of the code too, so you can check that out. All the codes, all the PPTs are there. Any doubts can be addressed. I feel no doubts. Let's go. Yeah. So the second topic which you came for is queues. Queue. What queues? Introduction of queues and circular queues. So queue is basically collection of data items with the restriction that data can be inserted from one end and removed from one end. So this means that there are two ends, one known as rear and one known as front. So from the front end we can remove the elements, from the rear end we can add the elements. So queue follows FIFO and LILO. First in, first out. Whoever comes first to the counter will get his order first. How easy is this? Last lady will get the order at last because she came late. Obviously, queues cannot be of infinite. Queues cannot be of infinite length. They have to be limited. They can't be standing around 20,000 people for a in a rotation. Before showing you the code, again there are some basic terminologies in queues like NQ, DQ, front, rear, and obviously overflow condition. So NQ means when we have to add an element to the queue, and the condition that comes is overflow. Overflow means when the queue is full. If there are only 1,000 tickets to be sold for a Shah Rukh Khan movie, there cannot be 1,001 people. Similarly, DQ is when we have to delete or we have to pop the element from the queue. That's not DQ. Underflow condition. If there is no person standing in the queue, what will the shopkeeper sell? Front and rear. Front, get the front item from the queue. Front is the first most element to be taken out from the queue, or it is the first most element that will be given the order, or that will be provided with the resource, whatever. So again, this is a queue full. The, all the people are standing. I've been like, so this is the front end from where this is the front pointer. We have two pointers in queue, front pointer and rear pointer. So the front pointer points at the frontmost element which will be dequeued, and rear pointer points at the lastmost element which was inqueued. So yeah, so I will just show the code and explain the code also. You'll have a better idea. Going with queue. So one more thing I had to tell you, I've again forgot. Yeah. So the thing is, during an queue, the front and the rear, the front pointer and the rear pointer are equal to -1. That means whenever the queue is empty, the front pointer will be -1 and the rear pointer will be minus. So let's go with the code now. So initially I've declared f as the front pointer, r as the rear pointer. They both are -1, and we are taking the size of the queue, as the queue cannot be infinite, as I told you, and we have declared the queue with its size. Okay, now we are again using a do while loop. I will just wait. I will Yeah. So I will just draw a queue. Two sized queue will be fine. 9 is so. This is the thing. This is the part. So initially front and rear values are -1. Initially front and rear values are -1. Let this be 0. Let this be 1. Solve the location. So I'll close this one. So we are taking the preference from the user that whether he wants to do in queue, DQ, display. Display is nothing but playing the whole queue in the same order. So case 1, which is enqueue. So we are taking the element, enter the element as input, and again we have to check an overflow condition that if r is greater than size -1, then the queue is full. If the queue is full, another person cannot enter the queue. Else if f is equals to -1 and r is equals to -1, remember just now I told you that f is equals to -1 and r is equals to -1 means that the queue is empty. In this example also I showed you that the f is equals to -1 and r is equals to -1, which means that the queue is empty. So what do? We put f is equals to 1, f is equals to 0 and r is equals to 0, and then we input the element, and it's ready. So this is the front and the rear pointing towards the 0th position, and the element I have entered is 9. Now if I want to enter another element, if we look at the conditions on the left hand side, this case 1 condition, we look at them, which condition do you feel will follow our figure? This is the else condition. R is equals to r plus 1. So the rear pointer, this is the rear pointer. Rear pointer. I will mark the rear pointer with a red pen. Rear pointer will move r plus 1. It will move at the next location and we will enter an element 8. Don't worry, I will show the code, all of this. We have entered the Sohail Aman Khan. This is not a webinar for time complexity. My friend Dharya took a webinar for that previously. You can check that out. So 9 and 8, and so this is the queue now. So next, now comes the DQ part. What is DQ? DQ is when we have to pop out the elements, or we have to take out the elements from the queue. So we have to check the underflow condition. The queue, if f is equals to -1, which means that the queue is empty, then what? Then the queue, obviously the queue is empty. Second condition we have to check is f is equals to r. If f is equals to r, then we have to take out the element and put f is equals to -1 and r is equals to -1. And the next thing which we have to check is an else condition, which we are there in this problem. Yeah, so we will pop out this thing, this element 9, and we will pop out this element 9. So let's just do that, then I will explain a very great. So I will pop out this element 9. Now what will happen? Now the thing will be, which will happen is that this 8 will move here. You can see that line qi minus 1 is equals to qi, which means that the value of the ith element is transferred to the value of the I minus 1th element. So 8 is transferred here and this becomes empty. And if we again do a DQ, this also becomes nullified and we are left with front and rear pointing to -1 again, and our queue is empty. Hope this is fine. I will just run the code and show you. So I will take the size of the queue as 2 only. I'll go for an inq. I will enter the element as 9. Again I will go for an inq. I'll enter the element as 8. I will again go for that. It could have shown 8 on 8 and 9, but here, since there are different places for entering and exiting, it is showing 9 and 8 as per the definition. So now just DQ the elements. We'll DQ them. 9 is DQ. So 8 is also DQ. Frontmost element 8. Right now. So this, I hope this concept is clear, or I will just brief up again upon that one. That and we have a lot of time. This is the queue. Don't go by the size of the boxes. I'll just, this is the condition which when we just have just dequeued, when we have just dequeued the 9 element from the queue. Now the 8th element is here. Okay. Rear is pointing here, and front, I'm denoting front by a blue line and rear by a red line. Hope it is visible. So now then the 8th element is here, front is pointing here and rear is pointing at 8 only. Now the element moves to the 0th position and 8 will come here and will get removed. And then rear will also point here only, will get removed. So now 8 is at the 0th position with the front and rear both pointing at it. And now we will DQ the 8th element also. So in a normal queue, the element moves from one position to another. Now you will be wondering what is a circular queue. I just wrote a circular queue. You will be wondering what's a circular queue. So this is queue, and now comes circular queue. So circular queue is a special type of queue. First, wait, I will just check if someone has a doubt. Yeah, Sohail, you can refer to that. Good to go, maybe. Circular queue. Circular queue is special type of queue in which the last position is connected back to the first position. So it makes a circle. Circular queue is also known as ring buffer. I don't know why it is known as. It is known as a ring buffer. And circular queue also follows FIFO and LIFO, the first in, first out, and last in, last out concept. So there are some more basic terminologies which I would like to discuss, and then we will straight away move to the code and end the webinar. It will take time. Yeah, just a pointer. So in this condition, in Q14, so we are front and rear are pointing at this. We are enqueuing 14 in this circular queue. Then we are enqueuing 22, so rear moves and 22 is enqueued. Then we enqueue again 13, rear moves, q minus 6, and the condition. This is the condition. So the size of the circular queue is 5. So now it comes that now we start to dequeue the elements. So first we dequeue from the front where the front is pointing. So the 14th element is dequeued, becomes this. Now the 22 element is dequeued, it becomes this. Front and rear comes side by side. Now we enqueue another element. Enqueue another element means that the rear moves here and this becomes the to the. Now we enqueue another element. So 20 is again enqueued. This becomes the condition. Now we enqueue another element 5 over here. Now you will be wondering what is the difference between Q and. So I will explain it using diagram and my. So let me make one circular queue. Perfect circle. So I will take the size of the queue as 2 only. Easy to explain. This will be 0. Will be again one more thing that the front and the rear pointers will be pointing at -1 during the initial. When the queue is empty, the front and the rear pointers will be pointing at minus. So initially the queue is empty, so the pointers are pointing at -1 over here. Yeah. So we go with the in-queue operation. This is the thing. Rear and both are pointing at rear pointer and front pointer. Okay. So let's see the left hand side. Left hand side shows that we are taking in the input of the element which we want to put, push, whatever. So if first condition is if f is equals to r plus 1 and if r is equals to size minus 1, then q is full. Obviously rq is empty, so this condition goes invalid. Second condition, else if f is equals to -1, r is equals to -1. This is our condition. This is the condition where the queue is empty. So what it says to do, it says that f is equals to point the f is equals to 0 and r is equals to 0. Let's do that first. Yeah. So we are pointing here. Now we will enqueue and value 9 in here only. Okay. And next we have to include one more value. I want to include one more value. So we come down here where it says else condition on the left hand side. Else condition, r is equals to r plus 1 and q r is equals to input. So we will, it is saying that we will go with r is equals to r plus 1, then we will into it for value 8. So currently this is the position which we are right now. Now comes a DQ operation. Now I want to do a DQ operation. Go to the DQ, case 2 DQ. So now if I want to do a DQ operation, what condition do I follow? First condition says f is equals to -1, r is equals to no element or the queue is empty. Obviously that's not our condition because the queue is filled right now. F is equals to r, that's also not our condition because I can two elements and both the arrows, the blue arrow and the red arrow are at different positions. That's also goes valid. Second condition is f is equals to size minus 1. Okay, equals to size minus, f is equals to size minus, that's also not the condition. So we go with the else condition which says element and we do f plus plus, pop up the element and we do f plus plus. So I will just pop out, we'll just get it here. Now it is pointing here and so now as per the condition, uh, both the rear pointer and the front pointer are pointing towards the 1th position element, that is, and the 0th position element taken. Now what I told you in Q was that the 8th element will shift to the 0th position, but the catch is that this takes a lot of time. The shifting of elements takes a lot of time. Time is money. So to save time, the concept of circular cube was built. In this condition, in this case, if we want to enqueue another element, no need to shift this 8. No need to shift this 8 from to the 0th position. Let's go up, see the code, refer the code. We have an option here, else if. We at the left hand side, third option, else if. Third option, else if r is equals to size minus 1, r is equals to 0, qr is equals to input, which means here rear is equals to how much? Rear is equals to 1, as you can see here. This is rear. This is rear. This part is rear part. This is at 1. So, and what is the size of the queue? I have taken a 2 sized queue. When I have taken, oh, good circle. If I have taken a 2 sized queue, it says that point this rear element, this rear element to 0 and taken the input. Let's do that. So instead of shifting the 8th element to the 0th position, I shifted the rear pointer to the 0th position and taken in the input. Now let's see if I have to dequeue and empty the whole queue, what will happen? Let's move to the second. So if now I want to empty up the whole queue, what will happen? Third else if condition on the left hand side says f is equal to size minus 1. Pop up the element. Print f, when we are printing the element, that means we are taking the element out, we are popping the element. And place the f is equal to 0. So we will take this out. What's that? Take this element also out. We have pointed like this is the condition. And now easily using our second condition, this else if condition, second one, we can easily pop or remove this 7, and this will again start pointing these both. Again, both. These both will again start pointing. Diagram becomes diagram. So let's see that same thing. Enter the size of the queue. Size of the queue was 2. Enter the preference. I will say I will enqueue one element. Let the element be 9 according to our. Yes, I want to repeat the process. Enter the preference. The preference will be in queue again. Enter the element. Element which I want to enter will be 8. In this condition which I showed you right now, just a minute. I should have saved that thing. So this was the condition. According to this, you can see this is the condition right now. 9. Yeah, this is the condition right now. So now what I will do, and this is the at the 0th position, this is at the first position. Now what I will do, I will just dequeue once. So the frontmost element comes to be 9. Here you can see, and nothing but I have dequeued this part. Now I will go for an enqueue again. So I have enqueued an element 7. Now, as I told you earlier, 8 doesn't shift its position. The pointer only shifts its position. That saves time. And 7 is stored over here. Now we are good to go. And according to our code, let's just dequeue it fully and I will show you. Top frontmost element is 8. Next again I want to do dequeue. Frontmost element is 7. 0. Over. So this means that circular queue is used to save time. Since the element is not shifted, the rear pointer is only shifted. So let's go back to PPT. Have I left something out? No, we are good to go. Any doubts can be put in the comment section. We are just going to end the webinar as we have covered all the topics. Hope it's clear. Any doubts? No doubts? Fine. End the webinar now. You can download the reference material from this given GitHub link, which we have also given in the comment section. For any further queries, you can contact any of our CodeChef member, or you can put them in the comment section below. And with reference to the person Sohail, you can refer to the video. If you still are not clear with your doubt, you can put them in the comment section. I will tell you the answer. Thank you for attending the webinar. Don't forget to download the reference material, whole PPT, all the codes, and a little bit of reference book which I was given by my professor. I have also added that for your. So thank you and the webinar.